there will be not too many people, then we will complete much quicker. Many pieces of materials. Did you get cold? I got some.
I noticed that. A little stuffier than usual.
So what we are doing, there is a preparation manuscripts, and we could wait longer time until it gets more developed, but if you start discussing and debugging earlier, it may get better. Well, I know it's a little ridiculous, but you may comment and criticize yourself as well. So the original idea was that we will get figures and captions, but it was some sort of last minute initiative, so those are only figures without captions. But we can go over and develop some ideas. How do you like or do you like this figures, or and make suggestions for future captions.
Mm-hmm.
And since it is only figures without paper, you can only guess what authors were thinking to put there. Can we go over the short manuscript by Aaron and discuss it? So I have some comments, but maybe you have something else. Discuss it, since there are not many people. We are not limited by squeezing thoughts. Mm-hmm. So there. Well, this first and second panels were great. For the spectrum, there is another feature which is not labeled, and PK reviewer will ask what it is. So we may, well, I mean the first author who is responsible for everything, may add additional label and generate the analysis. Like you already have works on particle in the box interpretation, which could be too much for this paper, but some traces of your particle in the box analysis can penetrate into here. So you may use your experience from this three-dimensional box analysis into here, and the transitions like in the there is a particle in the box progression for both electrons and holes, and there are states which we can name like S, P, and D, right? S is when there are no harmonics, just one lobe. Right, P yeah. When there is only one lobe in either of direction, and D when there are two lobes in sum. And each transition can be S to S, S to P, P to S, or S to D, this way. And they are progressing in increase. So it looks like the lowest one is S to S, and either third or fourth it will be P to P, which are expected to be strong by selection rules. And S to P or P to S are expected to have intermediate value of energy, and by selection rules they are forbidden. Therefore they are not so intense. But one can speculate that because symmetry is broken and not everything is ideal, they have traces in density of states. And well, if one would do density of excited states, probably there will be big peak here. But since they have low oscillator strengths, they contribute not substantially to spectrum.
I know in the hobby lab now, Sam figured out a way to get spectra, so there might be something to overlay on that, see if there's any similarities.
Yes, and if you have some experimental data, do not hesitate to work with it and just increase the list of co-authors. Mm-hmm. People will not mind it. And I will take negotiations on myself. Since you have access to data, just if you see something fitting, do it right away, because time is precious. Also for this figure, in figure 2, you do have dynamics in panels C and D, but it is not clear what is initial state, and probably because it is a letter paper, you try to present as minimal information, but one can put here by an arrow, where do you excite, mm-hmm. which will make it easier to connect and comprehend. Journal of Physical Chemistry now publishes color figures for free, but who knows if some groups will discuss your paper in group meetings and print it on black and white. These lines will be indistinguishable. So if it is not a big effort and you have a free minute, you may read through it with some dots and dashes.
Yeah, I probably made a new plot script for it that has everything in there, so I just have to change the types.
Mm-hmm.
probably redo the one I had at the.
Yeah, I don't mind, but you have seen that it was controversial in the group meeting, that some people were objecting. You may, well, again, it is your freedom of creativity, but you may build schematic diagram based on your understanding of particle in the box and combine particle in the box diagram with schematic of pathway of non-radiative relaxation. So I have several layers of meaning. But I don't care, it's your freedom. Well, would be great to label, since your spectrum already has labels like A, B, C, D, you can tell like omega sub C here, if it was what was excited.
Yeah, I just put those in as like templates to see how it looks.
Yes.
Update them with new
Oh
data.
yes. But, and sure you're planning to label access. Do you have plans for figures into supporting information?
Yes, these were the two that I have panels made for, but I have individual figures as well.
But can you remind what you use there?
Fluctuations,
Okay.
function on fluctuations.
Yes.
I think I was going to try to get MDPL, so we have some more experimental
Great.
data. Can you pull it up on the computer right now?
No. Just tell by words. You already presented the things on group meeting, something your oral presentation.
I was just
Anything
trying
else?
to remember what else I had.
Do you have, same as in the paper by Fatima that we are going through, did you have dependence of the cooling rate on excitation energy?
I do have that in the spreadsheet somewhere.
Okay, yeah. Nothing is mandatory, but it could be reasonable complement.
I know when I was looking at it, I think in the electron it had a constant cooling rate, independent of where I excited it. So
Well, in certain range, probably if you excited it too high,
I think I maxed out the limit of how many orbitals we had.
Okay.
So it became unstable at some point.
Okay. Also, I know I'm not. I'm too attached to the movie that changes.
Melody in there.
But since movies in supporting information are always brought up, one can make snapshots, like a couple of snapshots from the beginning and the middle, and put it as figures for supporting information. And if one day we need graphic table of contents, graphical abstract, and cover art, they would match there perfectly. Would you like to verbalize any of your comments?
A couple of questions. So the first one is why this work is special?
Huh?
Why this work is special?
Do not ask me, ask. And you can come here if you want to point on some figures.
We make qualitative connections to experiment and how in terms of quantum yield and in cooling rates by using an additional method that hasn't been previously reported.
So in this paper you will add lots of experimental data, right?
Yeah, so we'll reference that because we don't do any transient absorption stuff here. But I think one of the things I would put in is like those energy relaxation figures comparing the cooling of restricted and now it's been restricted. Because I know in experiment they see that there's kind of a long-lived state just above the band gap, and that's what we see with the spin orbit calculations and not with the spin restricted.
Okay. For the PL emission, so it seems the axis is not labeled correctly because you have emission below 0 electron volts. What's the meaning of that?
It's not labeled correctly. That's okay, got it.
Good eye, thank you.
I just put it in there to like lay out how it would look. And if put in more time.
And also for the density of states and also PDOS, why you just focus on very small regime? So the other feature doesn't matter?
Yeah, because we're essentially working or modeling photophysics. So that band gap of air is like spread of 4 eV, which is like within the limit of what you would do spectroscopy on. Not even a little bit larger. So those are like the most relevant states for cooling and for optical spectra.
For anything observed with visible spectroscopy.
Yeah, visible spectroscopy. And then if you expand it out, it's just other things aren't very resolvable. Like those subgap states near the band edges, they're harder to see. Because the further you go up, the bigger your density states gets, so it's, or the higher the peaks become.
First question of you will inspire me to ask. I think that if I would be a reviewer, what is the reference? What is to compare with? Like typically, if you present some results, you compare either different methods or different models. And here it looks like one successful method for one successful model.
Mm-hmm.
So it is successful in respect to what? You don't need to answer right now, but it should be in the paper or maybe in the figures or in supporting information as well. So maybe it is successful in respect to model without ligands, or maybe it is successful in respect to model with defects, or maybe it is only regarding methods. Maybe it is successful in respect to model without spin orbit, like without spin orbit. It is less intense photoluminescence, always transition.
Mm-hmm.
The work will be interesting and digested by community anyway, but for better digesting, it needs to be logical trend. Like it's not a set of data, but it is some story. You don't need, but if you have some ideas, what you are comparing, you can organize now.
At least one thing I was planning on, I think I mentioned earlier, was just the cooling rates, comparing spin orbit and non-spin orbit. I guess we can, in principle, do yields too, because I can't remember if I did yields.
You may have shown it in your oral presentation.
I mean, comparing quantum yield to spin restricted and spinor.
Mm-hmm.
I know I did the spinner. I don't know if I ever actually did it with the spin restricted. I'll have to check.
Just the way of logical construction of the paper. Even if your results are absolutely perfect, if there is like it is good compared to what.
Mm-hmm.
So one can intentionally prepare something bad and then compare and tell this is better than something else. A reference point.
Have you compared the electronic structure of models with and without ligands?
I have not. Well, I guess in some sense I have. Like I've removed some ligands and then let it re-optimize, then do calculations, but not completely bare.
Right.
I guess I haven't because I guess I didn't see a use for it yet. I guess that would be a reference. So I think it's in Svetlana's paper on ligand cooling rates is, I think that's how they got their reference.
You probably in figure 1 you have your cubic structure without ligands.
That was just done in VMP.
Yes, but do you have electronic structure for this Ligand vest?
I could do that. It would take
Much shorter effort than the rest of the completed calculations.
yeah.
And even if you don't include it into the paper, there is a very high chance that reviewer will not see and request it anyway. And then there is no question that without ligands, it will be very like vanishing photoluminescence. It will be like 3 orders of magnitude, or even more. And then it is kind of made up, but then you say, see what wonderful job ligands are doing.
No, yeah, that makes sense. So yeah, you can put that in the queue on yours.
Fatima, did you look through? Do you have any comments to?
Yeah.
Can you verbalize?
So these atoms, I don't know that there are different colors of atoms. I think the color should be mentioned. I don't know whether it's reasonable or not. And for DOS, I believe this one is partial DOS. So y-axis values are not visible. And for this figure, for electron dynamics figure, x-axis values and y-axis values, and what are the initial states, number of initial states are not here.
So the last ones, I just didn't do them yet because I was going to redo the figures.
Okay.
So those are just there to satisfy like how they would look if they were done. And then I missed the last part of your second for the PDOS, or partial density states.
Y values or y-axis values. Since this one is absorbance, right? This is density, just a different scale.
I think they have this. They should have the same scale. You're talking about figures B and D.
C and D.
C and
B and D, yeah.
D. They are the same scale.
Same is. So
Well,
D is same Y scale is C.
Not the same Y scale. It's zoomed in a little bit.
So I think Y values should be visible in D.
I guess I zoomed in because, well, if you go higher, the only thing you see is, like the black line is the total density states. So there's more density states from other orbitals, but the main ones to focus on are the ones that contribute the most towards dynamics, are just the ones in that -2 to 2 range with the Fermi level. And I just cut out the black line because it's not really providing much, and it gives better resolution for the other features. And then for your first question, I tried to put the color labels into the titles of each of them. So you can see for the CSPBBR title, like the CS is blue to correspond to like the little blue dots.
Oh, okay, I see.
It might be that they're just too small, so the colors don't pop up. That's how I tried to label them anyway.
But you can duplicate this information in the caption. Cyan, gold, and pink stay for cesium, red, and bronze. Done? Then submit it to
Thank you.
Hi London, how are you? So, these are boring parts of the game, so just sitting. That's fine, and you can criticize yourself. Maybe you got some inspiration since last time and have some ideas how to improve.
I think I'm perfect. Just as you.
So we have luxury of plenty of time. If you don't mind, we can discuss. Well, with the periodicity of these structures, we, I have minimal doubts or no doubts that the structures are correct, but there is a challenge how to represent them and to avoid confuses in readers. So if we switch on our imagination and try to project the periodicity, it looks like this row of atoms is identical to this row of atoms. It looks like which software do you use for visualization?
Vesta.
So it may do tricks on us. It may add atoms which do not belong to unit cell just to make it for better visibility, to show where are the borders of unit cell. So I would either remove these two or remove these two rows of atoms, or try to maybe not for the final figure, but for yourself, try to replot it with different software and see which atoms belong to unit cell. So another option would be to plot 3 unit cells, the central, +1 and -1, and then do this +1 and -1 in transparent. And then it will be clearly seen how this periodic structure is developed. So same here, the unit cell seems to include 3 layers, and if one goes, so this is diamond structure with tetrahedral, so this bond goes up, so it looks like these 2 atoms are these 2 atoms. So the software makes tricks on us and frivolously add atoms just for some reasons to make it for better visibility on the point of view of developers of software, which is not right. So would be again either to keep only 3 layers here and 3 layers here, or maybe add this transparent things. Would it be possible to just pull and expand this figure that it takes more space?
Then the aspect ratio will be changed.
Huh?
Then the aspect ratio will be changed.
Yeah, but the readers are literate, and they would follow not the visual impression of aspect ratio, but what are the labels, or just replot it in the panel, because right now it is very clogged. And if you want to focus attention on it, well, it is your decision, but it could be more for better visual.
Another option is I think I can. I can draw only the conduction band then. So I can draw the conduction band only.
Yes, conduction band only, and use it in portrait.
Okay.
Alignment and use all space.
And also, why the arrows are pointing to different directions? Like for the left panels, the arrows are pointing upwards, but for the right panel, it is pointing downwards.
Because the first left figure is radiative transition. Electron is supposed to travel from valence band to conduction band, and the right one is non-adiabatic transition. So electron is supposed to come from excited state to the band edge.
So for the left panel, you mean radiative transition is just absorption?
Yeah, electron will absorb for photon and will go to the excited state and conduction band.
Okay. Maybe different color. Maybe if it is so important, well, you may take time and explain it in details in the captions. I was playing peak and developing more things of secondary importance. Later on, you are making argument that there is a subgap here and subgap there, right? So there is
Density of states.
yes, in density of states. There is a because of this offset of the in the valence band for 1-on-1 and offset in between moving plus 1 and 100. There are subgaps which affect rates. But what is I don't know the answer, but maybe you have ideas or found it in the literature. What is the nature of this splitting? Why they split here substantially? And also, in analyzing this question, one may want to print orbitals. I don't know if you were doing it.
I have. Yeah, I forgot to
For
put it here.
for
I
information.
forgot.
I never saw them, but it will be. I will have a lot of curiosity. Maybe everyone in the audience. Up to now, we all were plotting orbitals which have index A, L, L, K at the end for all K points. Or if there is more than one, they are added together. But for here, one should explore VASP keywords to remove this option and make orbitals specifically for first K point, for second K point, for third K point, and they should look differently. So,
Yeah. So it was included in the molecular physics manuscript. The orbitals were included in molecular physics manuscript.
were made this way,
Yeah.
right? Okay.
Mhm.
But
In supporting documents.
so you may
I
well, I don't know if it is necessary, but if I would do this work myself in a systematic way, I would make like 1, 2, 3, 4, like 16 orbitals for valence band, 16 orbitals for conduction band, and just staring on them and looking how they are similar or different.
So right now I have only for HOMO and LUMO.
Okay, but try to. It
Okay.
may bring some scientific insights. I don't know which, but have you seen how Aaron was labeling his spectra? Peaks in the spectra, like A, B, C.
Yeah.
Right now, I don't have a clear idea, but maybe through discussions and while writing, or through orbitals, you can identify what is the physical nature of each peak, and maybe we can just label them and then refer to them. Even if there are more than one states under the peak, they may have some similarities in their nature. So even if we do not come with clear idea, we can just label like A, B, C or A prime, B prime for peaks. Ranges. We do not need this UV. So after 250, we don't care. We don't do UV things. And here it should be expanded to 700. Because your lowest band gap is here 1.8, right? And if you convert 1.8 electron volts gap into the wave numbers, it will be 690. So there should be additional peak which corresponds to the lowest transition, which would be reasonable to have here. And also same as when we were discussing figures, you may add, since on the next figures you show example of dynamics, you may show by arrow where do you excite, what is your excitation for the thing that you are analyzing.
It'll be easier to label your highest absorption peaks too. If you cut it off a little higher.
Yep. Make a note, because it's so easy to forget things.
And also here, the position of a subgap is suspicious.
Position of subgap or arrow to subgap?
Yes.
I would put arrow, subgap is between
Right.
peaks. I would put it like in here and in there.
Right.
There is a thing that so Fatima is author of a very important practical step that seems evident and clear, but since it is very new area and no one else did it, it would be better to explain in very basic steps how you label your states. So give equation and give maybe even example in a schematic diagram. So what you are doing, you are merging together two indices. One index for orbitals, which could be like Lumen plus 0, Lumen plus 0, Lumen plus 0, and index of k point, which is like k point 1, k point 2, k point 3, into one super index, like state 1, state 2, state 3. So you may want to make diagram like this and explain it. And give equation, which you use to label them, and add a diagram. It's very simple, but since it is very new, no one else did it, it's better to highlight your breakthrough, your methodology, because it could be useful for any person who would start to follow you in this research. And on the first glance, without preparation, it's hard to follow to the next figures without this explanation. So it may look childish, too simple, but it will really help to go further.
I had a comment on that too later, wouldn't it? Or could it be possible just to merge your LUMO and K value and just put the K value as a super index or superscript, like in front of the L, to try to condense it?
Yeah. Like LUMO with superscript 0, LUMO with superscript like 0.13, right?
Mm-hmm.
Yeah, could be. But since it was not offered anywhere else, one may do some really simplified, childish way in the first paper where it is presented, and then condense and make it more concise in next books. Because if one squeeze too much information on the first place, people may not digest it. But yeah, I like this idea. I'm happy. It's cool. It's not very visible. If one would do different background color, could be a little better, or maybe make yellow average line.
I was thinking, or like a comment that said white, we could do yellow or something bright.
Yeah.
I do have a question. So normally the expectation value dotted curve, it seems to be a little below with the population. Or usually they're kind of centered on top of each other.
Well, here it is superposition of 50 here, 50 there. If, then it will be in the middle. It's always a problem with averaging. If you were frequently listening to, I'm going to say something irrelevant to this figure, but if you were frequently listening to talks by our president, he explains why he hates Ehrenfest and likes surface hopping. He gives an argument like, if you are a pedestrian and you have a pool from the rain in front of you, you have a superposition of your potential trajectories to avoid it by going through the left side or through the right side. But if you make an average, you'll go strictly into the pool. And surface hopping, in some sense, avoids it. So it takes either one or another trajectory.
I guess not in the middle of the figure. I mean, so at time -3, you follow that all the way up. I know sometimes if you get too far away, or if your index is too high, it becomes kind of unstable.
Okay.
The energy calculation does.
Well, maybe 10 to -3 is already too long time and already some mixing does happen. If you would progress it to -4 or -5, maybe it will go away.
Yeah, that makes sense.
If you play picky, then the crossover from one regime to another regime, the point where it happens, could be related to features in the density of states. I don't know which, is it subgaps or this features which we may label like A, B, C, but this is open thing to discuss, and maybe while writing you'll come up with some bright ideas.
What's the meaning of all transitions here?
Huh?
What's the meaning of all transitions? This diagram?
I'll give word to the author. I think I understand, but she's a prime expert in these things. So what are all transitions?
So yeah, I think the band structure would be the good figure to explain this.
Huh? Should I bring up the band structure?
Mm-hmm. Yeah, here. So on the right figure, we can see electron can transfer from one K point to the same K point, red arrows. That is direct transitions. And all transitions it one K points to another K point plus one K point to the same K point.
So it's a combination of
Direct and indirect both.
Yes.
So transitions, direct plus indirect.
Combination of direct and indirect is what she
And,
labels as all.
Aaron suggested last time momentum restricted and momentum unrestricted, but it is hard to write in the graph. It's a mom restricted.
No, you can use this words like momentum restricted and restricted in the discussion section to bring, like, we don't need to make secret and big and trick tell like it is a no one else did it before and we don't know how to refer to these things, and there is a possible nomenclature to call them momentum restricted, momentum unrestricted. Maybe, who knows what readers would like.
They always do abbreviations too. You put
Okay.
too many of those and
Okay.
people get lost.
Yeah.
Ah, that's a good
So
idea.
it's hard to label everything correctly.
It will be UK, unrestricted momentum.
And also, I guess there is something wrong with the blue figure.
Here?
No, the blue figure. So if we look at the energy of the lumo, it is not consistent with the density of states shown previously. So right now it's like just like the first one, it's like 1 point something, 1.2, right?
Oh, so the it could be the procedure by subtracting between energy of orbital and energy Fermi can be done separately and with different constants. Like one could.
And it seems there is a huge difference.
Then probably one time it was the energy Fermi was not subtracted at all. I can easily imagine it. What's the value of difference that you have observed?
I guess it's like 0.6 electron volts.
0.6 in the density of states and about 1.3 in here, right?
Yes.
Yeah, this should be taken care of. There are two possible reasons. One reason is it is just processing things that can be fixed very quickly, and another one that during ground state calculations and during the molecular dynamics, value of Fermi energy may shift consistently. So all orbitals may shift. So there is nothing to panic about, but it's better to analyze it and find what is going on. Thank you for good eye.
For the rates figure, I think
Yes?
the y-axis should probably be renamed. Because the way it looks like it's an inverse picoseconds as a unit. We shouldn't have any units.
Yeah, and also it's a rate of
Wait,
time.
just a second. I would just move this bracket from here to there.
Yeah, I guess I would do that.
So
and then-
time divided by picosecond and then taking logarithm.
yeah. Maybe also put relaxation time in the subscript for tau.
Okay.
Or it might just make it, so like that's just a little cumbersome to read. Like you
Okay. Please make note because it can be forgotten through the discussion. Even sorry for.
It's okay. So here is time instead of rate.
Yes, it is time. Why we selected time? There are available data for both rate and time, and for fitting to have linear, to have the gap law, larger energy offset gives longer relaxation. So in sense of energy gap law, the linear trend is better observed in the time or logarithm time versus energy offset. So the strict energy gap law will just look like a straight line in this axis. So it doesn't deal with any science, it's just a better way of fitting in this system of coordinates. So it is not rate, it is time.
I guess I also have a question about the white vertical dashed lines
Vertical.
on the blue figures.
Oh, this white stuff?
Yeah. I guess what is that supposed to represent? Because it seems to me like that's supposed to be tied to the KE, but the KE should be a rate and not a time, and that makes me think it's a time. The dashed line does.
I would just put k sub e2 minus 1 or replace k to tau. Yeah. Fatima, do you agree?
Mm-hmm.
Yeah, thanks for good eye and please mark it explicitly. Because all these little details can be easily forgotten.
So what's the meaning of this white line, white dash line?
Can I try to answer? There is a procedure how the black dashes are converted into rate of relaxation. And it is already denoted in the methods. It will be denoted in the methods section, and it is clear. But some of the readers will not read methods section. They will go only through the figures. I can confess that I read many papers. And for such careless readers, it is a way, like visual way, how to correlate black line with either rate or time of relaxation that is reported in subsequent figure. So it is not rigorously, it is not necessary, but it is auxiliary tool to visualize things for careless readers. But am I representing it right? Okay.
So I guess I still don't understand exactly what it's representing then. Is that like is that supposed to be the lifetime of it? Or is that supposed to...
lifetime or relaxation time, how quick excitation goes from here to there?
If you assume it's a single exponential. So like once it gets down to 33%.
Yeah.
That's what it's supposed to represent.
So why is it in the excited state on one and then the LUMO on the other?
This question is not to me. Now it is time for first author to answer.
What was the question?
So like the one dash line is on LUMO plus 22, and then the other one is down on LUMO, I guess? Because if that's supposed to be a like a relaxation time, that just seems very strange.
Like, why on the rightmost it is closer to Luma, and on the leftmost it is closer to Luma plus something? Why it is not right in the middle? Is it artistic representation, or you literally took the relaxation time and put this vertical line based on the numerical data?
I just forgot.
Oh,
So it is
okay.
artistic representation.
Okay.
Okay, then if it is artistic, then try to make it in the middle if you think it is still needed. Otherwise, picky readers will protest. So when you were doing only 4K points, Luma and Luma plus 1 did have bigger offset, and Luma plus 1 and Luma plus 2 had smaller offset. When you do this, 16K points, the relative offsets between Luma and Luma plus 1 and Luma plus 1 and Luma plus 2 change. One may want to develop an explanation, because we need to justify that calculations with 4K points were sufficient. But if there were qualitative changes upon increase of the number of K points, we may expect that it will change also the conclusions. And there is no time to redo calculations, but we need to assess how much this error will be. Will it be something drastic and qualitative, or just minor quantitative corrections? But if you already found it, then we shouldn't hide whatever was found. Just analyze it, and in the next paper it can be taken care of by computing rates with more K points. Really everything.
I guess I have a related question. So can you go back to the table 1 at the bottom of the previous page, right here? So it seems key point 0.16 and 0.33. The data is pretty similar for both cases.
Mm-hmm.
So is there physical meaning why they're similar?
I don't know. I went first author to analyze and explain.
Or is this just a typo?
The difference is just constant. That's all I know. The difference between direct and all transitions, it's a constant for these 2K points. difference.
Oh, so you're surprised that this these two numbers are so close, and here these two numbers are so close. So, what are these numbers?
These are the
Those are so. Generally, I'm not sure if this figure is sufficient. Maybe we need to give more explanations, or at least maybe even highlight this by like yellow cloud and this by pink cloud to show that those are two different sets of data. And the number that Fatima is presenting in the table are the average offset between this set of data and this set of data. So it is some summary of their indirect transitions, or how Aaron called them, unrestricted transitions. So it's basically a main result of the paper, how strong role of indirect transitions is. And if we look on this figure, it looks like the offset for whatever k-point would be is approximately the same. So these both data sets are offset by several orders of magnitude. There is a question that we didn't resolve, and we may mention in the discussion section that Javed was raising. Like, how this would change if we make an effort to normalize everything. I don't know if you have still to.
I did. So what I did, I multiplied that below by the difference between these two k-points and divided by the total number of k-points.
Okay, and it still shows this orders of magnitude difference.
It's on the table. That order, but for
In the table?
yeah, for 3 k-points and not for 0, because I don't know.
Okay, but is it reflected in this figure? Did you have you made an effort to redo this figure after normalization effort, or not yet? Well,
I didn't realize that.
huh? Well, I don't care right now, but while preparing the whole paper, just look back on it. And can, if
So
you make
normalize means I need to do this for
Like divide
all
it.
the values. Then
maybe we should dedicate a meeting on the normalization. It's not an easy thing. It could be something like, if there are 4 k-points, 4 squared is 16, so divide on all results for indirect on 16, and all results for direct, just keep them as is, and then it will remove 1 order of magnitude. But I'm not sure. One needs to look with very sober eye. And okay. And we shouldn't delay developing of the written manuscript. We will edit through the iterations.
I still have a question about this figure.
Yes, please.
So it looks like for all k-points, all transitions are very similar, like the bottom part of the figure, right?
Wait. Please navigate me where to look at.
Just
Bottom
a
part.
solid
Down.
down one.
Yeah, down there.
So for at different k-points, they are all similar, right? Similar trend.
Okay.
But for direct transitions, it is not the case, right? So
So for the lower, the slow transitions are direct, and quick transitions are direct plus indirect. Am I right?
It's just opposite.
Opposite. Okay. Oh, okay. Shorter time direct. Yes.
I think momentum is just the initial condition, right? That's why I see we start out at a certain momentum and then let it propagate through all transitions. So you think, like, once you go a little bit further in time, they would find the similar paths. So the rates might be similar.
Maybe please record your idea. I'm breaking. And Yun, I do have a hypothetical answer to your question. When we are doing all transitions, direct and indirect, number of channels of relaxation is drastically larger. We scan through multiple offsets, and the number of it's like superposition of several channels that like screen through anything possible. And with such number of channels, there is less dependence on individual subgaps. So maybe there is a subgap in the original K point where we start from, but there is no subgap in the nearby K point. So in some sense, the direct plus indirect transitions is a way to avoid subgaps. Would it make sense?
Makes sense?
Okay. And then, if it is correct and we do not get argument against this idea, one can put it in conclusions. Like, including indirect transitions is a way to avoid subgaps for relaxation and to make the relaxation quicker.
Last question. So this time just the direct transitions. So why panel C are so different from panel D? Like in panel D, each key point has its own feature, right? Own trend, I mean. But in panel C, it seems there is a lot of similarity between different key points. Is there any physical meaning?
What was the question, please? Why they are different?
So in the 100, at larger energies, the trend goes down against the gap law for each K point. For 111, 3 of K points go against gap law and 1 goes along. Let's try to make connection through the band structure. I do not have exact answer, but there are qualitative differences if you look on the conduction bands here and there. So for 100, they are kind of equally spaced for each K point, and just this spacing becomes smaller and smaller as we go to a higher value of momentum. And here, for the first 3, there is a subgap that would affect transition after going above certain energy.
Mhm.
It is where the crossover from one range to another one. And for the last key point, they are equally spaced, and it seems that it should be same trend as we get higher and higher in energy.
Mhm.
I know what I'm telling is not clear. I don't have clear mind, but definitely one can compare density of states and these rates and make connections. The density of states, not density of states, dispersion diagrams for these two directions of growth have qualitatively different features, and these features definitely would affect the rates of relaxation, the pattern of subgaps and rates. And this paper doesn't have results for holes. For holes, this effect should be even stronger, which can be probably left to the next paper to continue. Any more questions to the first author? Okay, then probably let's submit the feedback comments back to the first author.
I think we have to transfer tables to this one knowledge. And also, this table is suspicious. So, these two columns are not correct. So, like this number and this number, or this number should be
Not much.
We didn't have a lot of time.
Yeah.
Okay, these two numbers.
Oh, I guess I was saying that. I didn't write them down.
This value is
No, I just look at this.
Say that again?
Oh, I was just saying I didn't
Double
write
check
much
all
on
the
there.
odds.
Oh, yeah.
It's basically like this kind of place, yeah.
Yeah, I thought of that too, but I still don't know why it's
So,
there. Yeah.
what should we do next? Next time we meet.
When is the next time we're meeting?
Friday or Tuesday?
For Friday, it will be different scheduling and different announcements. For Tuesday is like shorter numbers, with not everyone, only for papers ready. When will you have your figures and captions next Tuesday?
I could at least have like a good chunk of them.
Okay, yeah, let's
I mean,
do
I still don't know exactly like what I'm going to be including. I still need to actually dive into the models that I didn't look at in as much depth as I did on the poster, and see kind of what's going on with those.
Don't go too much away from poster. Just basically make a paper as a representation of your poster. Because if you try to diverge too far, you can postpone completion to next century.
Okay.
Just
So I should not worry about any of the other models, just the hydroxyl and the acetate.
Do not worry.
Okay.
We can do 10 other papers on other models. Let's complete whatever is ready in a quick mode.
Okay. Yeah, if that's the case, then
Yes,
I can
yes,
definitely have like, yeah.
And probably Aaron and Fatima can add the captions so that we don't rush too much. And then in 2 weeks, probably each of writers can compose the results section, right? Which shouldn't be big deal. Just add this. It's a extension of the figure captions. No objections.
No, that sounds good plan for that.
Okay. Yeah. I think we are in less Russian, more detailed focus on what we do compared to when we sit here with a bigger crowd. Okay, and Fridays will be more like show for coming to the front and delivering some fun stuff.
Are the meetings still going to be at 3 o'clock on Fridays?
You want other time?
Well, I work at the Math Emporium from 3 to 5, so.
Well, many people voted for 3. But when there is a bigger crowd, it gets up to 6.
Yeah.
So still be able to come. And writing is more important than speaking. Well, you will schedule a couple of time chunks closer to the end for you for like other models, and maybe for summary of equations that for like, collaborating with Alexander. Do not expect many results in this immediately. We will need to go over equations again and again and discuss. So it's a high risk, long run project.
Yeah.
Much more challenging than computational stuff that we are doing with this quick turnaround. Just so that it doesn't look like we are speaking foreign language. Originally, London is from theoretical group in physics that deals very successful computation of hydrodynamics, like liquid flow, and there are very advanced methods to solve how liquids go through pipes or how they mix and make turbulence. And in some sense, charge density that goes across interfaces also some sort of field that can be processed by the same methods. Mm-hmm. And the idea, it's very crazy, high-risk idea to merge together these two approaches and develop hydrodynamics type of equations for charge density on the interface of photovoltaic cells, which may or may not work, but if it will work, it will be something attractive to many readers. Okay, well, many thanks for investing your time and for coming either without any notice or on a very short notice. And, there will be an announcement, but it will not affect any of you. Most likely, presenter on coming Friday will be jumped. Second Friday will be Braden, who he already told it. He wants to speak, but not immediately. Okay. That's the cover. Meeting is dismissed.